Hello there. Um, Today we're continuing with our embedded Rust stuff. Um, so today I want to continue adding stuff to our little project. So far not so far actually. In the last time we added a LCD display to which we're talking over SPI, and that displays are counter variable that we modify using the timer tree interrupt. So then we're basically creating a string out of that using that dynamic data, counter data, and we print it out on the screen. So I actually wanted to add some buttons to the project, so that maybe we can interact a little bit with the screen or with the project, since we can now start display stuff. But I have a pressure temperature sensor here. It's actually it's a pressure, temperature, and humidity sensor all in one package, BME280, that uses SP or I2C protocol. So I was hoping that maybe today we can just hook this up and just display the data on the screen. So yeah, like I said, it's using the I2C, which is old and well tested protocol, widely used in embedded. So hopefully today's is going to be pretty quick. So hopefully we'll just configure the SPI pins, hook this up, and get it going. So there's one little complication here, because I know that there is a library, BME280. There's a Rust crate it's a driver for this sensor that we could use, but we won't, because the problem with this is that this library is using a delay, and this library is taking ownership of that delay. Measurements, this. So basically you need to provide the delay, and it will take ownership of this, as we can see here. But in our code we are actually sharing the delay in our idle task in here. So we are using it. We are actually using it to initialize the display, and we are using it in our tone playing function. And basically that was one of the reasons why, when we were building this, we didn't take ownership of the delay. We specify it as needed. We only take a mutable reference to it so that we can reuse the delay. Because the problem with the delay itself is, well, it's not a problem, it's just the way it is that the delay takes ownership of the system clock register. So basically, if we were to pass it to the BMP crate, we would lose the functionality and we wouldn't be able to use it in anywhere else. And it's further complicated by the fact that we're using the Arctic. And we cannot clone the delay. So because of that, I've made a fork out of this library. BME, and in here what I did change is that we don't take the ownership of the delay anymore. We only provide the delay in a similar way we've done it before with this. So that means that we can use this in our idle task and just simply share the delay as needed. So yeah, I guess let's just start from configuring the I2C peripheral, which we don't have an example here, but I think it should be semi-straightforward. So just to have a quick look, on this. So the crate that we're using for the STM31F1 processor or chip that we're using, it implements all of the traits provided by the embedded hull, and the embedded hull only specifies a blocking I2C implementation. So basically the STM, our whole crate provides us only with the blocking functionality as well, or the blocking implementation as well. So this is basically what we need to look. So in case you would just look for the I2C, in this case, at least for this crate, it's blocking I2C. And the other thing is that we need to pick the ports. So I think we can just simply go with the first two available on the first I2C1 instance, I guess. Yeah, so that means that, for example, here we definitely won't be using CAN in this project. I'd say we might use the serial maybe later on. So those two are a better choice for what we want to do. Yeah, so let's just get to it. So yeah, we need blocking. Okay, so this is where we were configuring our display stuff. And here is going to be our I2C stuff. So for I2C we need we essentially need 2 pins, and that's what we have on the module here. So we have the power supply, ground, SCL, SDA. There are also 2 additional pins, but I don't know what their purpose is on this particular module. Usually this chip or this particular sensor only comes with 4 ones. but yeah, in our case, I'm sure we only need the 4. And then let's just hook this up as we go. So yellow is the clock, and the clock needs to go to here, which is the PB8. So clock, yellow, PB8, and then the data chip PB9. So that clock is going to be PB8 and SDA PB9. Yeah. Okay, and then the power supply and the ground. Boom. Okay. Then the pins, in order to use them, the pins has to be configured as the alternate function open drain. So usually in here, what's the proper into alternate open drain. So basically, so far we were using the alternate function push-pull. So push-pull, it means that the microcontroller can essentially drive the pins on its own. But with open drain, the pins, they can only pull the pin state down. They cannot pull it up. So that means that the microcontroller will need on the 2 pins, it needs external resistors to be able to pull the pin up. And this and this chip already comes with pull-up resistors on it. There. So that means we don't have to put any extra resistors on the pins. So into alternate, no, it's open drain. And we need to specify the GPIO-BCRH register. Okay. So we have those. So now let's just configure the SPI instance. So to make it easier, because there's no way I'll remember all of that, let's just import it. What did I say? It's not SPI, it's I2C. It's I2C. So I2C, so we will want mode. I2C can operate in 2 modes. I think, what is it? Standard mode and fast mode. We will use fast mode. we should be able to drive it. So I think the fast mode goes as far as 400 kilohertz, and the other one maybe 100 kilohertz. Don't remember. We need duty cycle. This is for the fast mode. So it's the what's the portion of the pulse is high and which part is low. It's a similar concept as we saw in PWM. How much the ratio between the high pulse or the ratio of the time the pulse stays high or low. And we want the blocking I2C. And we probably will need this to pass the instance, I think. We're using 1. Okay, so blocking I2C, we want this, so that comes from the device peripheral, I2C. The pins is a tuple of the pins that we specified, which is the SCL and SDA. That comes from the alternate function IO, and it's the mapping register. The mode is what we were just talking about, the operation mode. What is it? Full speed? Let's have a look. It's so it's standard and fast, yeah. So not full, it's fast. And when it's fast, we need to specify the frequency in the duty cycle. So the frequency is 400 kilohertz, and the duty cycle is this. Okay, we need clocks, we need RCC, I think, APB. One. Start timeout, I'm not sure, but I guess 5,000 microseconds, yeah, so 5 milliseconds. Retries, I think 3 is a good number. Address timeout, so how long it will try to wait for ACK, I guess, after sending the address. Let's keep it the same. This and same. That should be it, I guess. So that only allows us hertz. Okay. So this. It's, I guess it's this. One? Okay. And that takes an ownership, but I think that's clone, so it's fine. So yeah. Okie Oh, so we have a collision of names. And yeah, that's because SPI also uses mode. Okie dokie. Yeah, so now we just need to import our the package. So let BME actually, let's import it. There. So new primary, it will just create it with the primary address or the default address of the chip. And we need to just provide it with the I2C interface that we've created. And that's it. And we need to initialize it. Init, and this is where we're going to specify the delay. There. Okie dokie. And now we can just pass it into our idle task. But we need to tell the resource struct this is what we want to do, to expect this variable. This, and that's going to be BME, and it uses the SRI2C instance. It's actually blocking I2C. There it is. Which is the I2C1 and then the pins. That's the signature of the type. So I2C1 and then the pins, and yes, we need to provide the type of the pins. So here GPIO B PB 9 and PB 8. Yeah. So type, and we need to import the open drain. Yeah, so that gives us SCL and SDA, and I should have define it here. Okay, and as we can see, it compiles cleanly. What's wrong with this? Unused result. So far we'll just assume that it's fine. And then BME, BME, and we need to tell it that that's what we expect to see in this task. There it is. And then so we can just then so the BME provides us with a function measure, which will return the measurements with those fields that we can query. So that gives us a result. Measure. So if we're okay, measurement, and we can, let's keep the counter working still. We're just going to do this. Yeah, just maybe 10 pixels lower, so 50, and that's going to be our temperature in Celsius, or new line, humidity in that's percentage, and then we want next line, and what is it? It's pressure, which is in pascals, I guess. So then we can take our measurement, temperature, yeah, measurement, humidity, and measurement pressure. Okay, that's oh yes, the function measure, because we've made that change. So yeah, we need to edit this as well, actually. So, but because we made that change, the measure function will take in the delay. Yes, the importance of updating the comments. There it is. Now we need to provide it with a delay. Like this. And then we can look at the error side. We can do the same. It doesn't implement the display. And we're good to go. And we can just display it maybe somewhere in the bottom of the screen. Does not need to be mutable. Okay, that looks like we're good to go. Oops. Yeah, we actually do need a release, because otherwise it won't. The code won't fit into our screen. It's initializing. And it doesn't work. So it just stopped. It just stopped at counter, but the counter doesn't display anything. So what can be wrong here? Okay, I think that the only thing that I think can happen is that if this is too long and it doesn't fit into the 16 bytes that we gave for that string here, well, which we used to display the text. So let's just see. Because that crashed our main loop. However, the interrupt kept working, so I suspect that this is the issue. It's not working. Okay, let's just check. Because we know that the other stuff is working and our interrupt is working as well. Yes, and that's what it was. And actually that's because I'm being stupid. The problem here is that we should have just cleared the text here, because otherwise we get the counter variable duplicated. So yeah, it's way better now. However, we have shitloads of decimal points, so I think we can just what's the syntax? Was it .2? No, it was something .2 colon. Just to display the 2 decimal spaces. Because it's the other way around. It's here. There it is. Okay. Oh, here. So, way better. So actually what we have here so far is a DIY thermometer, actually, high-tech, powered by ARM and Rust. So there, we already have something going. And if we, for example, kill the pin, it actually displays us the error. Acknowledge. I just removed the pin just to test it. However, it did crash the I2C handling and it hasn't recovered. Which is actually a little bit, that's actually a little bit problematic, and I don't think there is a way to recover from the from whatever is exposed from using just whatever is exposed in the I2C API. So basically all we can do is just reboot it. However, I haven't tried too much, I haven't played too much with the I2C handling, so I'm not sure what exactly is possible or how can this be done. So yeah, and one other thing that I changed between the streams is that I've changed the cargo config. So basically now just by running, by specifying the OpenOCD GDB file that we have configured, I can just run cargo run, which will compile the code and flush it into the chip and run the booger. So I just run with using just cargo. So yeah, I guess that's going to be it for today. Bye bye.